Hi everyone, welcome to video 5Q1. This is the first in a series of three extension type videos that are really going above and beyond what we are requiring of you guys from class today. So I just want to say thank you so much for being in the category of student that chooses to expand your understanding. So kudos to you, nice job. So the first thing that we're going to do is talk about this idea called the Pythagorean identity. And of course, Pythagoras is the Greek mathematician who came up with the Pythagorean theorem. But there is a particular identity or equation that is able to relate trigonometry into that Pythagorean theorem. And it's really necessary for you to understand where this theorem comes from, or this identity comes from, in order to view the next extension video, which is video 5Q2, and that is actually a proof of the Law of Cosines, which is the rule that we use and the equation that we use when we are dealing with a non-right triangle. So here we go. So this first example that you see here, instead of labeling the sides like they normally are, A, B, and C, what we're going to do is we're going to take out just scribble out the sides themselves, and we're going to just put on some sides that we use a lot in right triangles. And so we can think of Pythagorean triples that we're going to work with today. Which, remember, is a set of three numbers, and those are positive integer sides. Integer meaning sides that are not fractions or decimals. They are completely rational numbers, and Pythagorean triples are three positive integer sides that work together to form and to satisfy the Pythagorean theorem. So we have a 3, 4, 5 is one of the most common triples that we're used to working with. And so what I want us to do is I want us to sit ourselves right down here at angle A in this triangle, and we're going to talk about how it is that we can find the sine of angle A, and it's the sine squared of angle A is how you would write that, plus the cosine of angle A, and squared, is going to equal 1. And we're going to prove in this identity that that works. So first off, the sine of A here, sine squared A, as you can see it written out with sine and then the exponent squared A, really goes back to just the value of the ratio sine of A squared plus cosine of A squared, and somehow we have to get that to just come out equal to 1, which I know seems like it's not going to happen, but let's take a look at the picture real quick. If we sit ourselves at angle A, the sine, or the opposite, remember from SOHCAHTOA, opposite over hypotenuse, of that is just going to be 3/5. So if I square 3/5, and then I take the cosine of angle A, which will be its adjacent over its hypotenuse, which would be 4/5, and then of course I'm squaring that, is going to come out to be 1. Let's see if that's true. Whenever I square a fraction, I square the numerator and the denominator both. So I want to make sure I have 9 over 25 for this first fraction, plus 16 over 25 for the second fraction. And we want to know, does that equal 1? And the answer to that is, since we have the same denominator here, all we have to do is add up the numerators. And so yes, 9 plus 16 all over 25 does equal 25 over 25. And so, yep, that's 1. Check. Okay, so this next example here, if we go down a little further on the page, this middle triangle that you see, we're going to call this another triple that we know from Pythagorean triples, and that's a 5, 12, 13 triple. So I'll put those sides on. 13, of course, the longest side being the hypotenuse. And you can sit yourself anywhere in this triangle you want. It doesn't matter which acute angle that you pick, which corner. But let's just say we're going to sit ourselves right here at this corner for today. I also wanted to introduce to you a new variable symbol that we're going to use, and that looks like a circle with a line right through the middle. It's called theta, and it's a Greek letter, but when we use this Pythagorean identity, it's often stated as theta because theta just really means any angle. And if we use our Pythagorean triple idea over here and start thinking about putting ourselves up in this corner where we have our starred angle, and we wanted to think of the sine of theta squared, remember that's what sine squared theta reads as, plus the cosine of theta squared, and prove that that's going to equal 1 even with our 5, 12, 13 triangle. Then if we have sine, that's going to be 12, the opposite, over the hypotenuse 13. When we square that, then we're going to have the cosine of that same starred angle be 5 over 13. And if we square that, we get 1. And of course, squaring the fraction, top and bottom parts of the fraction squared, numerator and denominator, 144 over 169 is what 12 over 13 squared becomes, plus 25 over 169. And I hope you can see that if we add those two numerators together, because we've got a common denominator, all we have to do is say 144 plus 25 over 169. Well, look at that. We get again 169 over 169, and we get 1. So that's pretty cool, I think, personally, because it worked now with two triples. So then the last thing we're going to try, and this is what kind of proves it no matter what for us, we've taken two numerical examples. We're going to take a completely algebraic example here, and we're just going to use this bottom triangle where the sides are completely left as variables, and we're going to see if this works. So I'm going to pick this angle right here in the corner again for us to sit ourselves at in the triangle as far as points of reference for opposite, for adjacent, and for hypotenuse, of course. Calling that angle theta right in the corner. Then the question is, does still sine of theta squared plus cosine of theta squared, does that still equal 1, even when we don't have numbers to fill out? So what's the sine of theta if we look at it? Well, it's opposite over hypotenuse, and that's just going to be a over c. And then cosine of theta is going to be b over c, so we'll square each one of those fractions. The question is, are we going to somehow get that equal to be 1? Well, square numerator and denominator each time. A squared over c squared is what that first fraction becomes. B squared over c squared is what the second fraction becomes. And we still are asking, does that equal 1? Well, you guys, if we have common denominators like we've dealt with when we had number common denominators, now we just have variable common denominators. So we're going to go ahead and just stick that over c squared, both of those. And then we have a squared plus b squared. And we want to know, does that equal 1? Well, because this whole entire video is about, again, remember the name is the Pythagorean Identity, check out what happens when we look at the numerator. What do we know, you guys? That a squared plus b squared always equals. Always equals because of the Pythagorean theorem. So that's got to be a squared plus b squared is c squared. And when I take c squared and divide it by c squared, we're definitely going to get 1. So that just kind of shows you that that proof works out whether you're dealing with c squared over c squared, whether you're dealing with 169 over 169, or whether you're dealing with 25 over 25. It works out every time, you guys. And so that's why we call it the Pythagorean Identity. And that's just a little bit of background that you need when we're talking about the next video, like I said, video 5Q2, which is talking about how to prove the formula that we use called the Law of Cosines. So I hope you've enjoyed that little extension. Again, congratulations for just adding to your learning in that way. Great job, you guys. See you later.